Welcome, everybody. Thank you for joining us for Fast Track to a Clean Future, the first in ATSE's new webinar series, exploring technologies that can get Australia to net zero emissions. We're being recorded today, and we also have closed captioning so that anybody who needs that can utilise that facility as well. As we gather for this meeting from different places around Australia, I'd first like to acknowledge the traditional custodians of the lands from which we meet. I'm personally joining you today from Camaragal land, and I pay my respects to elders past and present, and to any Aboriginal and Torres Strait Islander people who join us online today. As we share and discuss our own knowledge and practices, we acknowledge the deep knowledge forever embedded in custodianship of country. I'm Catherine Woodthorpe, your chair for today. I'm a scientist turned business person, and I work across a number of sectors, in particular climate science and renewable energy. I'm on the board of Vast Solar, a solar concentrated thermal company, and Reliable, Affordable Clean Energy CRC. In the past, I chaired the Antarctic Climate and Ecosystem CRC and the Climate Science Advisory Committee, which delivered a report called Climate Science for Australia's Future, which Helen, Cleugh, one of our speakers, helped me with. And I was on the board of ARENA. In September, ATSE released its net zero emissions position statement. The position statement was created by an expert working group led by ATSE's Energy Forum and was refined by a consensus building exercise, drawing input and ideas from across ATSE's expert fellowship. With climate change as the #1 policy priority, ATSE is now embarking on a series of papers and webinars to draw on the expertise of ATSE's fellowship to share stories about the technology that can help Australia to net zero. As the COP26 climate change conference approaches, we'll be watching with interest and hope that Australia comes to the table when it comes to emissions reduction. We will hear from Dr. Helen Cleugh, Professor Andrew Blakers, and Scientia Professor Prasad at this first webinar about net zero tech. First up, Helen's going to give us an overview of what the climate science says about why urgent action to reduce our emissions is critical. Dr. Helen Cleugh is an atmospheric scientist whose career has spanned research, discovery, delivery, and leadership. Her research explores the influence of land-air interactions on climate, carbon uptake, and water availability, and how this affects carbon and water resource management, environmental outcomes, and climate. Her research has provided data, information, and knowledge for resource managers, urban planners, and decision and policy makers. And before we tune into Helen, I'm just going to introduce the other speakers, and then we'll move through them one after another. After Helen, we're going to hear from Andrew, who will talk about renewable energy solutions we have available today that can drastically cut Australia's emissions this decade from producing electricity. Andrew Blakers is Professor of Engineering at the ANU, where he founded the Solar PV Research Group in 1991. He was co-inventor of Sliver solar cell technology, the subject of a $240 million commercialization effort by Transform Solar. He was also co-inventor of the PERC silicon solar cell, which has 90% of the global solar market, and cumulative module sales of 100 billion Australian dollars. PERC cell deployment is mitigating about 1% of global greenhouse gas emissions through displacement of coal. Finally, Dio will present about sustainability in the built environment and how technology available today can help our cities reduce emissions. Scientia Professor Dio Prasad is among the internationally recognised Australian experts in the field of environment, sustainability, and decarbonisation. He has demonstrated expertise in delivering research to impact in large-scale industry, government and research collaborations. Dio has always worked in the applied field, and with qualifications in design, management, science and engineering, has a clear understanding of multidisciplinary approaches. After we've heard from all three speakers, we'll invite them all back to be on a panel where I'll moderate a question and answer session. Any questions you have, please submit them via the Q&A function at the bottom of the screen, and we will work through these during the second half of the webinar. So without further ado, it's over to Helen to set the scene, presenting on the climate science for why Australia should be working to reduce our emissions as soon as possible. Thank you, Helen.
Thank you, Catherine, and good afternoon, everybody. I'm going to assume you can see my front slide.
Helen, we cannot see the slide at the moment. Now we can. Perfect.
Okay, excellent, thank you. So climate change action, stronger emissions reductions by 2030, net zero emissions by 2050. These are all topics that are very much dominating the headlines, especially in the lead up to COP. Amongst all this commentary, it might be easy to forget the why, which is to limit human-induced climate change for a sustainable climate future. This requires mitigating future climate change to avoid the worst of the impacts and adapt to those changes that are already in train and cannot be avoided. My goal is to set the scene for today's webinar on the role of technology by addressing these 3 points with a focus on the latest climate change science from the IPCC. So the IPCC, the Intergovernmental Panel on Climate Change, was established in 1988 as the UN body tasked with providing periodic and impartial scientific assessments regarding climate change, its implications and risks, as well as options for adaptation and mitigation. It reports periodically, roughly every 7 years, and it does this via 3 working groups, a synthesis report, and occasional special reports. The Working Group 1 report on the physical basis of climate change was released in August. After an exhaustive and rigorous review process, this comprehensive scientific assessment was undertaken by a large and diverse community of scientists, including several from Australia, as you can see in this graphic. In fact, Australia has been involved through its science, through its modelling, through its observations in every IPCC report. I will now start to summarise some of the key headlines from this Working Group 1 report. So the first headline is that globally averaged surface temperatures have increased by 1.1 degrees above the 1850 to 1900 baseline. You can see the graph here showing the measurements from the pre-industrial era to the present. This rate and level of warming is unprecedented in at least the last 2000 years. And this is one of many lines of evidence showing changes in the Earth's climate system. This record, shown here, of greenhouse gas levels over the last 2000 years also clearly shows the rapid increase in the 3 major greenhouse gases from around 1800 through to the present. And down the bottom in the lower right-hand corner there, you can see the current levels and their increase over pre-industrial as per the report that was released yesterday. This inset shows the hourly variation in background carbon dioxide measured at Australia's Cape Grim station off the northwest tip of Tasmania. It shows CO2 increasing at a rate of about 2.3 parts per million per year now, which is almost twice the rate that it was increasing when measurements began in 1976. This is the curve that ultimately needs to be turned around by our collective actions. The 6th assessment shows that most of the observed warming is due to human emissions of greenhouse gases, offset somewhat by cooling from aerosols. The plot on the right-hand side shows this. It shows the warming due to greenhouse gases, the slight cooling due to aerosols, the net warming matching the observed warming. For those that are interested, this is the contribution from solar forcing, volcanic forcing, and internal variability. So the second headline then is that it is unequivocal that the recent warming of the atmosphere, ocean, and land is due to humans. These observed changes are widespread, rapid, intensifying, and unprecedented. They're occurring across all major climate system components, as you can see here, from the atmosphere to our oceans and to our cryosphere. It is indisputable, the third headline, that human activities are causing climate change. They're making extreme climate events, including heat waves, heavy rainfall, droughts, and extreme fire weather more frequent and severe. And our oceans are warming, acidifying, and losing oxygen. Global climate models are used to provide a view into the future of possible and plausible future climates. Modelling for the 6th assessment uses 5 illustrative scenarios of future emissions ranging from very high to very low, as shown here just for CO2. This plot actually shows these 5 emissions pathways in terms of the modelled global temperatures from 2015 through to 2100, with the best estimate of the temperatures by the end of the century indicated. Clearly, Future emissions cause additional global warming. Temperatures continue to rise until at least the mid-century. And it means that while this decade might be the warmest that we've seen in the last century, it is almost certainly going to be the coolest for the century ahead. In the near term, it is likely, in the near term, limiting warming to 1.5 or well below 2 degrees is difficult for all scenarios. It's going to take deep emissions reductions to meet these 2015 Paris Agreement temperature targets. But it also shows that meeting these targets is physically possible if we make rapid and large reductions in emissions. And this can be seen in the very low emission scenario where global temperatures slightly overshoot 1.5 degrees and come back down to just under 1.5 by 2100. Climate change is affecting every region on Earth. These changes and their impacts increase with every increment of warming. This is shown here for regional temperatures across the globe at 3 levels of warming, 1.5, 2, and 4 degrees. And it shows these incremental increases with every increment of warming. The same sort of changes are seen whether we plotted precipitation or soil moisture and the frequency and intensity of extremes. It means that if we cannot stabilise the climate at 1.5 degrees, then we should aim for 1.6 or 1.7 and so on, because every increment of warming that's avoided reduces the climate risks that we face. The 2020 State of the Climate report shows us that Australia's climate is also changing. The continent has warmed by just over 1.4 degrees since records began in 1910. This is for all months, for both daytime and nighttime. As a result, we are seeing more extreme daily heat events, with a 6-fold increase in the occurrence of very high temperatures. These heat extremes affect the health of our urban and rural communities, our ecosystems, their biodiversity, the productivity of our workplaces, our farms and our forests. Surrounding oceans are also warming by about 1 degree since 1910, and these increased and more frequent marine heat waves, along with the background ocean warming, is contributing to more frequent coral bleaching events, threatening the resilience and health of our coral reefs, as well as the health of our marine ecosystems and the productivity of our fisheries. Observed declines in rainfall and stream flow in South Australia have been linked to human-induced climate change, and the combination of lower rainfall and warming is increasing the risk of drought. We are seeing an increase in extreme fire weather and the length of the fire season. Combined with the lower rainfall and warmer temperatures, this is increasing our fire danger risk. More intense heavy rainfall events and rising sea levels around Australia are heightening the risk of flash flooding, coastal inundation and damage to infrastructure, property and coastal ecosystems, especially when these events occur together. So Australia is experiencing climate change now, and this is already affecting our communities and our industries. These changes will continue, and they will be larger with every increment of increased warming. Limiting warming to well below 2 degrees reduces the worst of the impacts associated with extreme heat, fire weather, droughts, intense storms, and coastal erosion. Moreover, slowing the pace of climate change provides us with more time to manage the risk and adapt to these changes. So we need to now go back to the global picture and the global carbon budget. The fifth headline then is that current and future warming depends on the cumulative emissions in the past and into the future of CO2. Every tonne of CO2 emitted increases global warming. The plot here shows the near linear relationship between cumulative CO2 emissions since 1850 and increasing temperatures. Observations and model simulations are using the scenarios that I've already described. This near linear relationship means that stopping warming means we have to rapidly limit the accumulation of CO2 in the atmosphere. It means that limiting future climate change requires us to reach net zero anthropogenic CO2 emissions by mid-century to stabilise global temperatures. It's important that we're clear on what we mean by net zero, so I've added a little definition there for you. It's quite likely, as we see in these emission scenarios, that effective and feasible negative emission technologies will still be needed to remove CO2 from the atmosphere. Limiting global warming to a specific level, such as 1.5 or 2 degrees, means staying within a carbon budget that is finite. For example, to have a 50% chance of limiting warming to 1.5 degrees, we've only got about 500 gigatons of CO2 left. On 2019 emissions, that's about a decade. This means that rapid, large, and sustained reductions are needed, including not just CO2, but methane and nitrous oxide, which are very important in the near term. These are all required to limit warming. Staying below 2 degrees requires at least 50% reductions by 2030, in line with reaching net zero by 2050. The longer we delay, the greater is the need for reductions later, the earlier we need to reach net zero, and the more we must rely on yet unproven negative emission technologies. Moreover, such delays burden future generations, the risks they face, the adaptations they'll need to make. The cost of actions to mitigate climate change now needs to be framed against these risks and the costs of unchecked climate change. The latter will be large for all sectors of Australia's economy, communities, and ecosystems. So to finish up, when I became a fellow a couple of years ago, I had to identify a challenge, a 2030 challenge for Australia. I chose navigating climate change and our transition to a low carbon future. And I spoke about the role that ATSE and technology can play. And there's 5 things I pointed to. The first 4 I put here because they're perhaps not what you're thinking of. It's to show that technology is critical across the value chain, from our observations, from monitoring, reporting, and verification, from our computing systems, our software and hardware, to simulate the climate, to share and make accessible and make relevant climate information so it can be used by decision makers, and to support the global activity that is the science through partnerships, cooperation and collaboration. But of course, today is really about those technologies that are going to enable us to rapidly lower net greenhouse gas emissions. This includes negative emissions technologies, the role that agricultural practices can play in reducing emissions and increasing sequestration. The clean energy in our built environment and our industries and transport, efficiencies and reduced emissions, I know that Deo will speak to. And of course, the very last one, and this is where I hand over to Andrew, is of course the role that renewables must play in our electricity sector. So while we hand over to Andrew, thank you for your time. I'll just finish with these wise words from the IPCC. Thank you.
Okay, so my message today is that we can get rid of 80% of emissions easily, cheaply, rapidly. There's nothing mysterious about it. It's only the last 20% of emissions that we actually have to do some serious research development and commercialization. First point to make is that solar and wind won the global energy race. They are 75% of global net capacity additions last year and 99% in Australia. So new generation capacity is basically solar and wind in most of the world. And in over the next few years, that'll go to sort of 90% of new capacity additions will be solar and wind. Look at fossil and nuclear. It's stuffed into a box which is only half the size of wind and much smaller than solar PV. Second point to make is that balancing high levels of solar and wind is really straightforward. It's not hard. There's so much nonsense spoken about how it's hard to balance variable solar and wind, and the solar and wind is not always available, and blah, blah, blah. First thing is that having solar and wind is highly desirable because one is often available when the other is not. The second is you spread the collectors over 1 million square kilometres or so, for example, the eastern seaboard of Australia, which is exactly what's happening. That hugely reduces the amount of storage by smoothing out local weather and demand. Third point is shift loads from night to day. At the moment, we heat water in the middle of the night in water tanks. That should be done during the middle of the day. Your electric vehicle, when you purchase it, should be charged in the middle of the day, not in the middle of the night. And finally, there's quite a few options for mass storage, pumped hydro and batteries being by far the most important. So I'll talk a little bit about off-river pumped hydro energy storage. This is a storage system where when the sun and wind are available, you pump water uphill from a lower to an upper reservoir. And in the middle of the night, when you need that energy back, the water comes back down through the tunnel and the pump turbine to recover that energy. And the round trip efficiency is about 80%. That means you only lose 20% of the energy in the storage system. Batteries are a little bit better at maybe 90%, but cost far more. And so for overnight storage, pumped hydro is 99% of the global energy storage market. So this little system here with a combined reservoir area of a square kilometre, 100 hectares, upper and lower reservoirs together, is a gigawatt power rating for 6 hours, and no rivers were dammed. So at ANU, we did a global off-river pumped hydro atlas. We found 600,000 off-river pumped hydro sites with an enormous amount of storage, 1 million gigawatts for 23 hours, all outside national parks and urban areas. In Australia, we found 4,000 good sites, mostly down the Great Dividing Range, but in many other places. That's 300 times more than needed to support 100% renewables. So this is a graphic of an area maybe down the Araluen, and there's hundreds of similar areas. The amount of storage you see there is enough to support 100% renewables for the whole of Australia. And there are 4,000 other sites that you can also look at. So, of course, you wouldn't put all your storage in one place, but it's just to illustrate that Australia has vastly more pumped hydro, off-river pumped hydro than it will ever need. If you look at facts on the ground, new Australian energy infrastructure to support the rise and rise of solar and wind, it's all about pumped hydro for energy. Snowy 2.0 is under construction. That's bigger than all of the utility batteries in the whole world put together. On the other hand, if you want short amount of storage for sub-seconds up to a few hours, it's all about batteries. Batteries and pumped hydro go together extremely well. Batteries are for short, high power applications, pumped hydro for overnight and longer. And finally, transmission is critical to bring the new solar and wind power to the cities. Importantly, not a single one of the dozen or so pumped hydro systems under consideration involves a new dam on a river. It's just not required. So let's look at the renewables deployment speed per person. For a bunch of countries, this is in terms of new watts per person per year. Australia, Netherlands, and Norway are well out in front, installing solar and wind at about 3 to 5 times the per capita rate of China, USA, Europe, and Japan. Remarkably, Australia is right up there, and this is despite, not because of, the Commonwealth government. There has been some help from the state governments, but overwhelmingly it's technology push. It's the compelling economics of solar and wind that is rolling right over the top of Commonwealth government preferences and policy. So that's having a major effect on the national electricity market. What you see there is the market over the last 4 years or so, and the yellow area is a projection into the next 18 months. The green is the solar, wind, hydro. Overwhelmingly, it's new solar and wind, and you can see it rises and rises pretty much consistently. Black coal falls and falls. Brown coal falls whenever a new brown coal power station stops producing. And as for gas, that's the grey area down the bottom. Gas-led recovery, I think a laughing gas-led recovery would be more appropriate. Gas is simply not very relevant to the current or future electricity grid. A lot of people think that as you bring more and more solar and wind into the system, prices go up. Wrong, prices go down. The more solar and wind that we put into the electricity system, the lower is our electricity price. What you see there is the red line of the electricity system going up and up in terms of renewables. So we're currently at about 36%. The blue bars are the market price, wholesale spot market price. And you can see there was a sharp reduction from 2020 onwards as a new solar and wind flooded into the market, with the exception of the second quarter this year when there was a fire at the Cleugh coal plant, which instantly took it offline, and a flood at Yallourn. And that led to this unscheduled sudden loss of 3 gigawatts of coal led to a spike in prices, which is still echoing around the system today. However, in another quarter or so, that will all be washed away as ever more solar and wind flood into the system. The take-home message is, if you want cheap energy, put in more solar and wind, because it's the cheapest energy in history. Let's look at an 80% cure for Australian emissions, getting rid of 80% of Australian emissions using entirely off-the-shelf technology. This is a pie chart of where Australia's emissions are. So electricity is about 33%. It's really straightforward to replace that with solar and wind. Stationary energy basically means low and high temperature heating. That's the role of electric heat pumps and electric furnaces to get rid of gas. Electric vehicles can get rid of oil from the transport system. And when we stop exporting coal and gas, then we will get rid of the fugitive methane that arises from coal and gas mining, and that's another 10%. So you can basically look at the current 500 megatons of emissions in Australia today, and 400 megatons can be got rid of easily using off-the-shelf technology from vast production runs. And there's 100 megatons of somewhat harder reductions. So let's have a look at the various targets. In 2005, which is Australia's baseline year, 300 megatons was 612 megatons was supposedly emitted from Australia and carbon dioxide equivalent. Last year, it was a tad under 500 megatons. The Paris target gets us down to 450 megatons. If we are to match the United States, European Union, and United Kingdom COP26 target for 2030, then we need to get down to about 300 megatons in 2030. The current federal government has declined to do that. It turns out that it's actually rather cheap, rather easy to do it. I don't know why they don't, well, I think I can guess why they don't proceed to do what is the right thing, and will save money. So the Commonwealth Government has now agreed to a net zero in 2050, and you can see a bunch of years along the bottom from today up to 2050, and up the side is the emissions in megatons for each year. So it starts off at about 500 megatons last year, and it'll be much the same this year and probably next year. We can go to net zero via the current Paris target, and we'll emit 8.6 gigatons of emissions, or we could move immediately to a 300 megaton target in 2030 to match the US, EU, and UK, and that gets us 5.6 gigatons of future emissions. That's a 3 gigaton difference. That's a really significant amount of CO2 that we should not emit. The easy sectors are electricity, vehicles, heating, and getting rid of methane leakage. Harder is aviation, shipping, land sector, metals, and chemicals. If we get onto the easy sectors straight away by electric vehicles, solar and wind, and electric heaters, then that buys time to scale up to get rid of the harder sections in the 2030s. So this is just a bar graph of the 2020 emissions sectors. You can see electricity is, and stationary energy and transport is most of it. We can drastically reduce that by 2030. The Commonwealth Government released its COP26 statement recently. There's two good things in there, and a whole bunch of things that should have been in there were not in there. Zero by 2050, well, whoopee-doo. That's way out in the never-never. There's no plan to get there. There's a 50% reduction by 2030 would be appropriate. It's not in the statement. The statement talks about low-cost solar PV. Well, that's good. It's going to happen anyway. But it does not talk about wind, transmission, storage, electric vehicles, and electric heaters, which is actually what's required to be done in the 2020s. This is the easy sectors. Why aren't we getting on with it? There's a lot of magical thinking about carbon capture and storage and soil carbon and new technologies and carbon offsets. This is all about keeping the current coal and gas system operational. Australia in COP26 is going to be a resented freeloader, and quite rightly. So getting down from 500 down to 100 megatons is really straightforward. Mature technology from vast production runs, solar, wind for generation, transmission, pumped hydro, batteries and demand management for balancing, electrification of transport and heating. This is all very straightforward. We don't need new technology, nor taxes, nor carbon capture and storage, nor hydrogen, nor a gas-led recovery, nor all the other distractions that are currently being pushed. In summary, Solar and wind are already 3/4 of global new generation, 99% in Australia. The more solar and wind we get into our energy system, the lower our prices of energy. Balancing is really straightforward using off-the-shelf technology, and Australia is showing the world how it's done. We can go from 500 megatonnes last year to 100 megatonnes in the 2030s via renewable electrification of transport and heating, and that buys time for the last 100 megatonnes. So this is the fastest energy change in history. Let's get on with it. Thank you.
Hi. There's a few questions starting to come in, and the one that's been upvoted the most. But actually, I'm going to go to one on Helen, which is really quite an interesting one, which is talking about so, you know, you've set the scene for the science, but we also get the internet full of so-called science that suggests otherwise. Can you give us a couple of tips about where some of that irrational or wrong science is coming from, and how to deal with it when we get people throwing it back at us and saying, oh, but I read that?
So there's a simple answer, really, I think, which is, this point about the science being settled. Of course, scientists are always asking questions and probing and wanting to learn more about the system. So the word settled sometimes has the wrong connotation for people. But what the science is clear about, and I can't remember the numbers on that second slide that I showed, but climate science has been investigating more forensically, more deeply, more comprehensively the state of our world's climate and how that's changing for over 40 years. Sure, there's some things we still don't understand, but the clear consensus view, or consensus, I don't even really like that word, that the science is just so clear through multiple lines of evidence about the results that I just showed, that I think one needs to, then when one reads something on the internet, weigh that up against tens of thousands of scientists saying this is what we're seeing, this is what the observations are showing. You can't argue with the observations. This is what our best analyses are showing in terms of what's causing these changes. So I think it's a matter of just thinking, which are you going to believe?
Yeah, and you don't even need to believe it's the observations which tell it. At the end of the day, the science explains why the observations are what they are, but the observations are absolutely unequivocal and pressing. We also have had somebody asking, and this is one for Andrew, about whether we should include wave energy in the tools for reducing CO2. It's something we looked at a lot in ARENA, and despite the apparent obviousness that it should be something we should include, from what we saw at ARENA, there's a long way to go before the technology's there, but maybe Andrew could make an observation about that.
Leave it to the market. If the market accepts, if wave energy makes it in the market, then good and well. It's just simply another technology. At the moment, it has zero market share. Catherine, I can just keep answering questions. Jet fuel. Jet fuel is almost certainly going to be synthetic jet fuel, simply because it's too difficult to change engines away from kerosene. And this is basically hydrogen from electrolysis driven by solar and wind, carbon from the atmosphere, again driven by solar and wind. Jet prices will go up a bit, but then that's not going to impact poor people because they don't travel by air. Those of us who do should pay for it.
Yeah, and somebody's referred to the cost of heat pumps and so on, but we actually have heat pumps. They're called air conditioners, and we use a lot of heat pumps. It's a matter of where the electricity to drive them comes from. So the same air conditioner that cools you in summer in the middle of the day when there's a lot of solar energy coming on my roof will also be the thing that will warm me in the winter.
So Catherine, if you want, I can answer another one that's come in. It's not near the top, but Rowan wanted to ask about water vapor, and I can just answer that quite quickly and simply to say that those effects are absolutely included in both our analyses of the observations of the climate system, but importantly in all of our model simulations. And maybe just a quick comment on wave. In addition to what Andrew's just said, yes, the market will decide. It is interesting to note that scientists are exploring the role that installing wave energy generators can also have in minimising some of the impacts of added energy in the ocean and in the waves, and therefore reducing some of the impacts. So there is actually multiple benefits of wave energy. And I'm not sure whether the market will respond to that, but I just wanted to make the point that wave energy is something that is being looked at in places like the Blue Economy CRC. Back to you, Catherine.
Yes, and indeed things like bores coming up to 7 and those sorts of types of waves, which are reliable and consistent. Dio, we have your presentation.
Great, thank you so much. I had a mix of slides up for our second meeting at 1 o'clock, which were confusing things for me, but thank you so much. I'm going to talk about just the built environment sector. By the way, I'm talking from Gadigal country of the Eora nation. And my talk narrows things down to a sector which, as Andrew said, is one of the easier sectors perhaps to deal with. There's a lot of work done in looking at this sector from aspirational perspectives, but what I'm going to do is, after a lot of data collection, try and put it in the context of some good science and numbers. Just as a starting point, Australia-wide, as you can see, this particular slide is more than 24 hours old, and there is no targets at the time of writing for federal. But states are driving quite a bit, and coming from New South Wales, I'm seeing significant opportunity being grasped by New South Wales in terms of driving and capturing the technologies and opportunities for next generation of jobs and growth within that sector. However, we wish to just focus on the built environment sector, and globally, there is a lot of targets being set. A lot of these are aspirational, but many of them are beginning to nail down how it would work, what technologies we have and how they might be applied to bring it down. And we have done a similar exercise in the Australian context. The Global Alliance for Building and Construction, which is the UN body that came out at the time of COP in Paris, has now looked at international numbers and said that net zero for operational life of buildings is possible by 2030. And it may run over a bit towards 2040 for embodied carbon, which deals with materials and technologies and things that are where carbon is embedded in their through their manufacture. World Green Building Council, a major body in the world driving change, Royal Institute of British Architects and American Institute of Architects, all the architects who are driving change by good design and planning and so forth, are setting professional goals that are very much in the short term, 2030 goals for net zero, and some overruns into 2040. In Australia, for example, the Green Building Council, the National Australian Built Environment Rating Systems tools they use, they are very much on path to driving reductions. The construction code, even though not fully appreciating the use of renewable energy at the moment, but there is a plan for a trajectory towards net zero energy buildings, which will deliver a lot of change. The peak industry body is on board. The ASBAC, in line with the commitments that were made, and other cities like Sydney and Melbourne have their own net zero carbon building agenda, and they are using their mechanisms and tools to be able to drive that change within city levels. So what are we talking about when we say net zero carbon in buildings? We are looking at now whole of life. It started with just looking at, okay, energy efficient lighting or cooling and heating and so forth. The debate has moved much further and looking at whole of life, not only to the end of life of the building, but how do you design and plan so that beyond that life, the issue of circular economy, how can we get circularity coming into this so that the next life of the building is also being able to use, reuse, reproduce materials for the next generation of building products and so forth. So we're looking at embodied carbon and operational carbon to actually think about true accountability in terms of carbon. In simple form, when we build through demand for energy in operational life and carbon and embedded carbon, we have emissions, And in terms of going net zero, we're trying to bring it beyond that number through efficiencies and best performance on-site renewables, and off-site renewables. A lot of this is beginning to kick in. This is just an example at UNSW, where I come from. They did a mapping across the campus. It's a large energy consumer, and looked at its demand profile. It then invested in a solar farm, photovoltaics, and as Andrew said, photovoltaic products coming out of Australia at Andy and Martin Green in the building that you see at the bottom left of the slide comes from that, and 70 to 80%, even 90% by estimates of PV applied there had its origins in Australia. So we can develop technologies that capture these, and we generate enough in the day to then be able to offset nighttime use as well. But as mentioned previously, when we bring in storage at the right time, we are able to do much, much better than that. So these are transitional approach before we start having all the technologies, etc., to be able to allow us to navigate better towards net zero. What we looked at the network level, and as Andrew said, 80% can go towards renewable. We looked at a attribution. We looked at how much renewable energy in the grid can be attributed to buildings, and through that, looking at what remains in a bottom-up approach. So through good design systems and all of that, to be able to, and there's a lot of data available to us in this, and how we can achieve best performance that can allow us to navigate to net zero carbon very quickly. So our office building, most people classify as a difficult one to deal with. Class 5, so CZ5 is what we're talking about. The typical average consumption at 138 kilowatt hours per meter squared per annum. Through tools like Neighbors that I mentioned, it can be brought down very quickly to 110. And our numbers show that we can take it down to 66 to 72 kilowatt hours per meter squared per annum. And at that level, offsetting with green power and on-site and off-site renewables becomes a much easier task. As you can see in this diagram, the red line coming down to net zero from the current average. But if you start before looking at best performance and targeted performance of our numbers, we can navigate through efficiency generation and offsets through renewable energy very quickly to net zero. Similarly, embodied carbon for a premium office 2021, we have typically 3,900 or so kilogram of carbon per meter squared net lettable area, down what's trajectory towards 2030 of 1890, and then renewable energy offsets that take it down to zero. We have set a goal with the Institute of Architects in Australia to drive this challenge for building sector, so that from 2021 to 2025, we have all the standards, codes, and mechanisms in place, knowledge and promotion, so that by 2030, we are actually delivering definitely on all operational carbon down to zero, and then or at the same time, many of the buildings can go down to net zero in an embodied carbon sense, but some complex ones may overrun past that date. So here's a challenge that we have set based on good numbers, and we think we have all the guidance documents. The CRC I chaired has many documents that allow you to actually follow steps towards how quickly and how cost effectively we can drive low carbon. While we are doing that, there is a lot of information emerging on other problems like urban microclimate issues with increasing temperatures, how planning deals with it. And you probably know about Eastern Sydney and Western Sydney differences in summer at peak time is huge. So we have done a lot of work looking at roofs, for example, gray roof on the left there, top left, and white roofs. What is the impact and opportunity there? Greening and also looking at water bodies in planning and cool materials and pavements, etc. And what level of reductions in temperature is possible so that they don't convert to additional cooling load, if you like, in buildings, and as a result, offset some of the gains we are making. Together with that, we have looked at demonstration villages like this particular White Gum Valley in near Fremantle, which is a community looking at on-site renewables and high efficiency design and community renewables, and together with tools that were developed in the CRC, like peer-to-peer trading system that Gemma Green there in the picture led and got the big Global Disruptor Award a few years ago from Richard Branson there, who hosted that particular award, that it can, not only in Australia, but it is now in a number of countries trying to deliver high levels of renewable energy integration within buildings. And together with tools like this, which came initially from some work that done at the CRC, but has evolved a lot since then, where it showed that 52% of PV systems were underperforming. So tools like this allow you to detect and fix those problems so that you at least are getting the performance that you planned for. In addition, we have also looked at a whole bunch of evidence through better design, net zero buildings, net zero precincts, to be able to provide evidence to governments for better policy. And in this case, just one example where a Victorian government kickstarted a policy in the area of zero energy homes through the evidence provided by one of our living labs in Perth that I showed. And as a result, it can be shown that we can deliver on net zero carbon built environment by 2030, largely, and with some overruns. There's a guide coming out and a book later this year that has a lot of the details in here embedded in there. So thank you very much.
Hi, thank you very much. Now, I note that Dio does have to go at 12:55 on the dot. So if you see him suddenly disappear, don't panic, it's not a technology problem. He's got back-to-back meetings. So we've just had Helen set the scene on the science, which paints a picture that can look daunting at first glance. But then Andrew and Dio together have shown us how it can be done. Andrew's been busy away on the Q&A answering things directly, which has been very productive. I also want to comment, there's been a lot of comments in the chat area about politics. And something I want to say, I said at the press club last week, as citizens and as scientists, we need to be clear about our expectations of our governments. And I don't think it's political to tell our government of the day, whoever that might happen to be, what we expect of them. And I think that certainly there's been a clear understanding from the whole of the Australian populace that that's what they're looking for. So I really don't see them as political as such. It's just that's how democracy works. We tell our governments what we want them to do. So I'm going to see, is there a question for Dio before we run away? If not, I have one for you, Dio. So to deliver on net zero carbon buildings by 2030, we need the professions to be on board with this and have the capability and understanding of high levels of efficiency in design. It's something that at Race for 2030 CRC we're also really conscious of. Do you think this is a problem, a drag on our ability to resolve this, or can we carry out rapid capacity building to get them there?
I think we can. There is a lot of capacity building going on at the moment, both in professionals who are in practice, but at the university tertiary education for the next generation of people. We know that there is a climate emergency, if we call it that, so that we need people in short term to be able to deal with better design and be really into the low carbon element of the design that we are talking about. I am very confident that we can have the workforce and professional capability to be able to deliver. I think the tools are there, the benchmarks and targets are there. How to do information is coming out quite rapidly. You mentioned RACE, but also the CRC before that in low carbon living has delivered a whole bunch of information, and it can be done, I think, in the very short term.
And energy efficiency is a huge proportion of that as well.
Yes.
There's been questions on technologies and also just more generally, and a few people have ticked this one off. What's the impact on regional Australia of Andrew's easy path, and how should we mitigate their mistrust of a city-based academic solutions, Andrew?
Regional Australia is going to do extremely well. All of the solar farms, all of the wind farms, all of the pumped hydro, all of the transmission, most of the batteries are going to be in regional areas. And this equates to tens of billions of dollars of investment every year for the next 20 to 30 years. Apart from a few heavily coal-dominated seats, which we'll lose because coal will become less important, all other regional areas are big, big, big winners. And in particular, if you happen to live anywhere near high power transmission, you are a really big winner, because that's where the solar farms, the wind farms, pumped hydro will go preferentially.
Thanks. Helen, I've got a question. What effect did COVID-19 have on global emissions reductions? It's something I think a lot of people are wondering, with the lack of travel, both commuting and of course even more so air travel. What do you think that the impact has had? Have we been able to observe it yet?
Yes, so the analysis has been done on the reduction, or the effect of the reduction in emissions due to the slowing down, if you like, of everybody during the COVID lockdown, particularly in 2020. It's an interesting result, actually. The emissions reduction, I think, was around, I haven't got the numbers right in front of me, Catherine, but I think they were around 7% reduced emissions of CO2. But it was very short-lived and not even seen. Actually, if you take that amount of carbon dioxide and turn it into parts per million of concentration in the atmosphere, it is so small that you don't see it within the variability that we have of our record of CO2. So it was short-lived and it was small. There's a couple of other things, if I may, that I'd like to make a comment on, though, regarding COVID. We also cleaned up our atmosphere. So we reduced air pollution. People could see the hills for the first time. And that actually had a small but observable warming effect, because aerosols cool the climate. So it was kind of an interesting year, because it shows a case study. It shows how large the challenge is, but it does show that human behaviour affects the atmospheric concentrations of these gases that affect our climate. We can do it, but it's clear that the changes that are required are quite major in terms of, our whole system has to change. The kind of shifts that Andrew and Deo are talking about, because COVID, that small decline was simply not enough. It was short term and was not sustained. So, but it's just to reiterate my point, I think it provided a few interesting lessons for us.
It did. There's been a few comments about agriculture, but of course Andrew didn't touch agriculture. He left it well and truly alone in terms of your percentages of what we can do now. So I don't know if you have any thoughts on that, Andrew, given that there's been some questions, but I do note that you didn't actually say that that's an area we should immediately be slashing our carbon emissions in.
Well, of course, we should stop land clearing once and all, decisively end. However, we need to get on with the easy 80% and not let the fact that we don't yet have complete solutions for the last 20% stop us getting on with the easy 80%. If we get on with the easy stuff, it buys us time to do the R&D and the scale up to address the last 20%, aviation, shipping, the land sector, and so forth. Let's get on with the easy bit while working on solutions for the hard bit.
It all comes down to that budget that Helen described and that I talked about last week in my talk as well, that we have a budget of CO2 to put into the atmosphere to hold the temperature down. Every 1 gigaton, 1 ton, 1 ounce of carbon we don't put in now is 1 more ounce of time that we've bought to solve some of those trickier problems. So I'm absolutely with you about do the easy 80%, take the low hanging fruit, because we all can do our bit. And it's not just markets, governments can do their bit, helping energy efficiency in homes of people who wouldn't be able to afford to do it themselves, to put that initial investment in, which of course then saves them a lot of money longer term, but it's the initial investment a lot of people don't have. So there are many ways, many levers that governments can also do to assist this to get moving more quickly.
And Andrew's right also, just, you know, there's important R&D that's going on right now about reducing emissions in agriculture. And that's really important that we keep doing that. We can, as they say, chew gum and walk at the same time. And I think, you know, I know CSIRO and others are investing in, you know, low emission feedstocks and so forth. So there's, you know, the role that precision agriculture can make, etc. So there are some important R&D. And I've just noted in chat that there's going to be a webinar on this, so I'll stop talking because the experts will talk about that later. But I just wanted to echo Andrew's point that it doesn't mean we just stop doing the R&D. We can do both. We can do the easy stuff, the low-hanging fruit, while we invest in some of the R&D that we're going to need to get to that harder space that Andrew mentioned.
And I'd like to pick up, you made a comment about technology, Helen, that I think is so important. We see technology being thrown as being the answer, and we immediately equate that with just big ticket things, carbon sequestration or whatever, wind farms, better solar. But we forget the technology is the data, the understanding, the modeling, all of those bits are part of that technology that we actually need to help us get there. It's just all parts of a massive whole.
Yes, we've got a lot of climate change and climate variability, and the nature of that variability is changing as well, coming down the pipe at us, and we desperately need better modelling tools to enable us to provide those early warnings on a seasonal, multi-year, decadal timescale. There's new science that needs to be done, and the technology plays a huge role, especially some of the recent advances, not just in the hardware of supercomputers, but also machine learning, artificial intelligence, that's transforming actually the climate modelling space, and those are just as important in some ways to provide that information that society is going to need to manage the risks of climate going forward.
I think that's a great way to finish. We're right on our time, so I want to thank all of our presenters, Dio in absentia, Andrew and Helen. It's been a really, really interesting set of presentations. I hope everyone's taken away something that they can do better or that they can help others do better, and that we are all actually working on this together. We don't just leave it to others. It's incumbent on all of us. Thank you very much for your time today. Thank you to ATSE for hosting this. We'll look forward to the whole series of webinars that ATSE has. So stay tuned to their website for more details about future webinars. And thank you.